Hello, I'm Simon Brightwell, and I'm going to talk a bit about protecting pipelines in a changing environment, and in particular the role of wireless condition monitoring as a way of helping to identify and mitigate geohazard risk. Changing climate conditions are resulting in extreme weather events becoming more frequent. These are resulting in relatively long-term, gradual effects, things like deformation of the ground due to changing water content or thawing permafrost, but also sudden events which can cause failures due to landslides, for example, or debris flows, flooding and soil erosion. So it's not really just professionals involved in the industry that are concerned about these factors, but also some of the authorities, some of the respected bodies. People like the PRCI have documented their concerns, and as we can see here in this bulletin of June 2022, they're joined by the US Department of Transportation, who were expressing their view that earth movement, particularly in areas of variable, steep and rugged terrain, can give rise to a threat to the integrity of a pipeline if those threats aren't identified and mitigated. And when that happens, when things are not identified and they're not mitigated, the consequences can be costly and damaging. This particular site in Texas in 2020, a slope gave way after a period of rainfall, rupturing a gas pipe, releasing nearly 150 million cubic feet of gas, causing an explosion. Fortunately, no loss of life at this site due to its remoteness, but a costly mistake nonetheless. This particular site in South America, Ecuador, 2023, saw a large-scale slope failure of an unconsolidated rock slope due to erosion and undercutting by the river Marca whilst in flood. This led to the closure for a period of between 2 and 3 weeks of 3 strategic oil pipelines, which led ultimately to the cessation of Ecuador's oil exports throughout the period of this closure. So the economic consequences of that would, it goes without saying, be pretty extreme. But these things aren't always sudden. They can be slightly more incremental. And the example in polar conditions, in permafrost conditions, where pipelines were built and designed for ground conditions which would, to all intents and purposes, remain frozen, but are now subject to seasonal thawing, localized thawing, which is placing challenges on the foundations and increased stress levels on the pipes and particularly on the welds as a result of this sort of differential and unplanned thawing of the permafrost. Particular problems on slopes, of course, where creep can take place, but in an environment that is both remote and vulnerable, this is a significant area for concern, and any data that can help to mitigate that concern can only be valuable. So there's a whole bunch of different ways of gaining that sort of geodata, and I think rather crudely I've listed these from the small, detailed, localized, precise view at the top through to the big picture at the bottom, where you've gone really from manual measurement and attended survey at the top down to remote sensing techniques that could be conducted from the ground or from an airplane or from satellites. So really there's a broad spectrum of data. They've all got their advantages and limitations, but what I particularly want to dwell on now is this middle ground, really, where wireless monitoring I see as being one of the techniques that can cover pretty large areas, quite extensive areas, quite quick and easy to deploy over areas that are covering hundreds or thousands of meters, or large areas, but also are able to provide high frequency reporting, high frequency sampling that, for example, satellite INSAR cannot do. So that middle ground, that gap between the big and the small coverage techniques, I think is an interesting territory. And the role of wireless is one that I think should be explored with that regard. For those people who are unfamiliar with the wonderful world of wireless monitoring, there's typically three components to a system. There will be a suite of sensors. There will be a wireless communication platform, something that allows those sensors to talk to each other and to communicate with you as a remote stakeholder. And there will be some sort of online portal that allows you to see what's happening and to make some interaction and manipulation with the data. And this is what some of the sensors will look like. There's a growing fleet of sensor types that is available and can be used to gather data on geotechnical or structural and environmental properties, both at the surface and in the ground. In most situations, there will be a role for tilt sensors. They are a core part of many deployments of wireless monitoring. The tilt sensors down here in the bottom left corner, the three of these together, a family of Senceive nano tilt sensors, quite handy little devices. They each contain a MEMS sensor that is capable of measuring rotational movement to an accuracy of about 1,000th of a degree, which will equate to sub-millimeter accuracy in most situations. And I think if we take things a stage further, having established that you've got a robust, proven set of instruments that can be deployed at remote location, then in the particular aspect, the particular application of slope monitoring, then I'd like to just focus on the InfraGuard solution that has been developed by engineers together at Senceive and originally at Network Rail, the UK railway operator, who were very concerned about the risks posed by steep slopes affecting, disrupting and causing danger due to landslips on the UK rail network. So InfraGuard is an integrated solution that brings together a range of sensors, typically including tilt sensors and cameras, to provide both incremental monitoring of long-term movement and detection and very, very rapid warning of sudden failures. At the core of an InfraGuard system is the Senceive flat mesh tilt node and the rather cunning set of sensors that are within this that allow it quite uniquely to operate in a low power mode for many, many years. For example, reporting every 30 to 60 minutes for in excess of 10 years with minimal maintenance. But in the event of movement, it can behave quite differently. And we'll just have a look at an animation to see how that can work. Here's our friendly little tilt sensor, and here we can see it being mounted onto an array of stakes on an earth bank. And in this case, that bank is perched just over a valuable pipeline. In the normal condition, when there's no movement, it'll be reporting on a preset frequency and reporting back to you by the cellular gateway that you can see in the front left corner here. That could be a SATCOMS link in a remote site. If there is small scale movement detected by one sensor, that will send an alert and it will trigger a photograph. The other nodes in the system will continue to operate at their preset frequency, and you've got the option then to take a look at the photograph and see what's happening. If that movement develops further, however, and you get a higher magnitude event affecting multiple sensors, then they will all switch to near real-time reporting, multiple photographs and high-level alerts will be sent to you via SMS and email, along with everybody else who you registered on that system for that site. So this allows you to gather that combination of gradual long-term movement together with sudden event detection, such that well before you're able to get boots on the ground, people out to site, you're able to know where something is happening, get an idea of its scale, and to see photographs of it that will not only, of course, tell you roughly what's happening in terms of the severity, but will also help you to identify false alerts, because people will lose confidence in a system that is providing multiple false alerts. So if we move on, we can see here a couple of data examples. In the first case, at the top here, we've got a 12-hour view of a site. This happens to be a railway site in southern England. And through most of those 12 hours, nothing really much is happening until at this time, 2:42 in the morning. It always seems to be 2:42 in the morning when people are trying to get their sleep. That the slope gives way, and you've got this sudden spike picked up by the tilt sensor. But what I particularly wanted to highlight here was not just that spike, but the fact that the system, for a period of up to 4 days before this, was also picking up detectable, distinct anomalies in the data, a series of steps. Some of them, the first one, 4 days before the landslip took place, involved movement of close to 30 millimeters in just a few minutes. So had we been on the ball here, we were able to detect those signs, those warning signs, and in the case of a pipeline, that could well allow us to get out to site to inspect it 4 days before the failure, and possibly to shut the supply off at that location, or possibly to take some remedial measures to relieve that risk. In this particular site, it wasn't a pipeline, it was a railway, and you can see the effects here of several hundreds of tons of earth and sand and rock sliding down the slope after heavy rainfall, and some of that deposited on the railway line just by this tunnel entrance. So I hope that in this short little explainer that I've demonstrated that wireless remote condition monitoring is a solution to consider as a way of identifying and mitigating geohazard risk for pipelines. It's quick to install, it's simple to set up and operate, it provides high frequency data from remote locations, and those data are both precise, reliable and repeatable. They can include measurement of movement, but also a whole lot more with the ability to combine geotechnical and structural sensors into the same network. And for those reasons, then I think it can be a very useful asset management tool, something in the long term, to allow you to detect early signs, get early warning of a problem, and in the long term, in terms of asset management, to predict and prevent, to make your maintenance and intervention much more efficient. In terms of environmental impact, then I think that if it's possible to mitigate those risks, to detect a problem early, to stop supply through a pipeline, then that will help obviously reduce the scale of any failure, the magnitude of any failure. It will demonstrate due diligence. It will help build support in the community and with agencies responsible for future authorization and compliance and licensing and so on. And for a combination of those reasons and others, I think that it will provide a positive impact on the bottom line, because failures are expensive, and anything that can be done to reduce their magnitude can easily be paid back. So I hope that that's a useful little explainer. We'd love to tell you a little bit more. Please get in touch if you're interested. Thank you.